So welcome everybody to today's class on comparability graphs and permutation graphs. I'm glad to see all of you here, both in the classroom and in cyberspace. Let me first review what we studied and what we learned up to now, or mention a few things. In the opening first lecture, we introduced a variety of intersection graphs, and some of those were interval graphs, graphs of paths in trees, circles on arcs on circles, maybe even circles on arcs. We introduced the chordal graph property and the TRO property. We studied chordal graphs for 2 lectures now, and today we are moving on to the TRO property, the transitive orientation property that defines a class of graphs called comparability graphs. We talked a little bit about the hierarchy of these families, and in the course of next week, we'll talk a bit about the hierarchies within chordal graphs, like block decomposition, BD graphs and RBD graphs. And of course, in all of this, we talk about algorithms for various optimization problems. Some reading that you can do if you would like, which is highly recommended. As an introduction, you could read chapter 1 of the book Tolerance Graphs, which is on my class website, but is a book by Martin Golumbic and Anne Trenk. And you can review some of the basic algorithms that everyone probably knows from from their previous courses, and chapters 1 and 2 of my book Algorithmic Graph Theory and Perfect Graphs. Today, as we go into comparability graphs, TRO, transitively orientable graphs, these are the sections that are relevant. And for permutation graphs, the second half of today's lecture, there are the sections indicated here in my main book. What is a transitive orientation? It is a directed graph, an orientation of an undirected graph G, obtained by assigning directions to each undirected edge such that the transitive property holds. That is, if in the orientation F, X goes to Y, Y goes to Z, then it must be that X goes to Z. Sometimes we say that F squared is contained in F, where F squared is the paths of length 2. Every path of length 2 is shortcutted by an edge in the orientation. And a graph that has a transitive orientation is called a comparability graph. Now, in order to obtain transitive orientations, we use something that we call the forcing relation. We'll define a binary relation gamma on the edges, on the orientations of the edges, in fact, of a graph G, where AB is gamma related to A prime B prime, if and only if the first vertex A and A prime are the same and B prime is not an edge, or B is equal to B prime and A prime is not an edge. Let's look at a piece of a drawing of that so you can see. The first situation is that A and B are an edge. A prime, which is the same as A, goes to B prime, but there's no edge between B and B prime. The other situation is analogous. A, B, A prime, and B prime are the same. Now notice, if you're going to get a transitive orientation, this is a crucial structure. We might call this a V, or if I turn the paper like this, maybe a gamma or a lambda. but we called it gamma because it looks sort of like a gamma. Like a gamma. This is the gamma relation. And why is it important? It's important because if you were to orient from A to B, it would force this direction, A prime to B prime. If it went the opposite direction, I would have a directed path of length 2 with no possibility of a shortcut. Similarly, on this side, if you determine one orientation, it forces the other orientation if you were to hope to get a transitive orientation. So that's why it's called forcing. Back to the slides. Now you see it again. We say that an edge AB and A prime B prime are gamma related. There's a forcing relation if this configuration happens. And this is an equivalence class. If we take the transitive closure of this gamma relation, which we call implication classes. What do I mean by the transitive closure? Well, it's the usual transitive closure, and here's a definition. Look at the blue line. If AB, say that's A0, B0, is related forced A1, B1, that forces, in turn, A2, B2, and so forth, up to AK, BK. That means that, which we'll call CD, that means that A eventually, AB eventually forced CD. A, B, and CD are in the same implication class because one orientation for one implies, through this chain, a orientation for the other. And since we are considering these as directed edges, we clearly have that either a set of edges A intersected with its reversal is empty, or they're equal. And the theorem goes that if G is a comparability graph, then that will happen if and only if every implication class A has the property that A and its reversal A minus 1 have nothing in common. Their intersection is empty. And this will give an algorithm to recognize comparability graphs, but it doesn't immediately give a transitive orientation. For that, we have to move a little bit further. Let's look at an example by trying this on a triangle. Let me draw a triangle. This is about the simplest. Okay? Is there anything forced here? The answer is no, because you don't have this configuration where you have a V with a missing edge. No edge is missing. So here, nothing is forced. Nevertheless, I could say that the implication class would be each edge separately. They themselves satisfy that property, and so this is a comparability graph. It has a transitive orientation. I just don't know how to get it. Let's look at a different graph. Let's add one more pendant edge to it. Now here's a little bit more interesting graph. Now there is some forcing going on. Here, for example, this edge on the top forces this edge on the side, one way or other. Similarly, on this bottom side. But the bottom edge is not forced by anybody. The red edges by themselves give you transitive orientation, and the blue also. Let's see what the algorithm that I would like to propose is. Start off with a counter I equal 1. Repeat until no edges remain the following loop. Pick an edge and orient it in one way or the other. I pick the edge, call it EI. We start with E1. Give it an orientation. Generate its implication class, which we'll call BI. Test to see whether it and its reversal are empty or not. If they're not empty, I will have some conflict and I will fail. Otherwise, I increase the counter. I remove the edges. This is crucial. I remove the edges that I've painted or oriented, and I continue my loop again. Take another edge, generate its implication class, test it, remove it, and so on. This iterative process goes on and on. At the end, I'll put them all together, my oriented edges from the first iteration, second, and so on, call that F, and that will be my transitive orientation. And let me remark here that the number of iterations of this loop is invariant. That is, no matter how you make your choices, the number of iterations is always the same. This was kind of surprising. It was surprising for me after I ran it on a bunch of test examples by hand. And I wondered why. And the reason I had to discover is that there is underlying this a matroid structure that would have to be discovered. It was hiding and it had to be discovered. Let's look at a few more examples. Here on the left, A, you have a transitive orientation. This forcing was fine. B, this graph does not have a transitive orientation. And starting with AB, that's this top edge, if it goes up, this goes down, this goes up, this goes over, this goes down, this goes up, and that would force this original edge to go down. Uh-oh. I get the contradiction. My algorithm fails and declares this is not transitive orientable. Now, both of these graphs are transitive orientations in one iteration. The first and the second. Let's see an example that requires several iterations. Well, let's first do it on our graph that I have on the sheet of paper in front of me. This graph has the red edges forced, the blue edge forced, but they don't force each other. The algorithm says, choose an edge. Let me randomly select an edge. Oh, this one. Okay. Let's randomly suggest, flip a coin, up or down? Down. Down. That forces this up. This forces this down. Nothing else is forced. I remove it. Up, down, down. And what's left is the graph with that looks like this. One edge. Well, this is pretty easy to continue the algorithm. I pick this edge, I give it an orientation arbitrarily, and now I put them together. I take the union of red and blue, and what do I get? I should really be doing this more colorfully. Okay, up, down, and all around. Here, there, and everywhere. I put it together, and lo and behold, this is transitive. It's not really a lo and behold, there's a proof for it. Here's a more complicated example taken straight from the book. If I have this graph here on the left as my starting, and if I choose the edge AC to start with, that's the edge up here, I give it an orientation, say down, AC forced this side forces that side. here are my forced edges. Nothing else is forced. I remove them, and second iteration starts with this graph. This, I arbitrarily decide to choose BC. That's this bottom edge going across. I arbitrarily decide to make it up. That forces BE. That forces, in turn, BD. But it also forces B to A. Now, notice in the original graph, that wasn't the case. In the original graph, BE did not force BA. But the removal of these edges in iteration 1, suddenly there is more forcing going on. This triangle is now missing some edges. So now this is what is forced. Remove it, and all I'm left is a single edge CD. I choose it, I orient it, and put the pieces together, just like Humpty Dumpty, except here, when Humpty Dumpty fell off the wall, I can put the pieces together and get him back with its transitive orientation. Okay. There's the following theorem justifies it, which we won't prove here. You'll have to read the book to see the proof. If G is an undirected graph, and we have this decomposition into implication classes, then G is a comparability graph, has a transitive orientation. If and only if the implication classes are mate-wise empty, the forcing classes are mate-wise empty, and every circuit of edges V1, V2, V2, V3, and so on, such that you don't have triangulated chords, must have even length. Condition number 4 is actually the traditional first characterization of comparability graphs given by Gilmore and Hoffman and Guila-Uri. The more algorithmic characterization started actually with the paper from Pnueli, Lempel, and Even. Amir Pnueli, as many of you might know, was a Turing Prize winner, so a pretty smart guy. And I started being interested in this when I read that paper and said, well, I could do a little bit better. And what's this thing going on that there's this invariant number of iterations going on? And that was basically my first major piece of research, discovering why, understanding that matroid, and studying more problems on comparability graphs. Well, fine, we have a transitive orientation. Let's try to do something with it. Let's try to color comparability graphs. We can do so by defining a height function on the transitive orientation. So let f be this orientation that we've obtained, and let us define the height function as follows. So you see that height function is going to sort of go from the bottom to the top. H of a vertex v, the height will be 0 if it's a sink. As you go up in the hierarchy, the height of v will will equal the maximum of the heights of all its children, that is, all of those vertices that it sees. So you start at the bottom of the hierarchy, and you then give the height to the next level and the next level and the next level in a very standard fashion. Now, any acyclic orientation has the property that H will always properly color the graph. Each of those height will be a color. Height 2 will be color 2. Height 5 will be color 5. But that height function on an acyclic orientation may not be optimal. The number of colors being used will equal the number of vertices on the longest path as you go up the hierarchy. However, if f happens to be a transitive orientation, then this coloring is optimal. Why would that be? Because if you look at a path going, say, from a sink all the way up to a source, well, because of the transitive edges on that path, it itself will be a clique. So because it is transitive, each path corresponds to a clique. So you might ask, why is it optimal? Because every path is a clique. Now, what's going on here? It's the same proof that we saw with interval graph coloring and with chordal graph coloring in the following way. We've succeeded to color with the number of colors in the longest path. The longest path is a clique. So you would require at least that many colors. Hence, you've done it optimally. We can do more with this height function and this and looking at the hierarchy of the orientations. We can easily get a maximum clique from this, can't we? Because a maximum clique, the largest clique, will be the longest path. So you could do a depth-first search and find the longest path. If you do a depth-first search, you can easily find the longest path. You can also solve the problem of maximum weighted clique. Give every vertex weight, or you could do this either vertex weights or edge weights, let's say vertex weights. Then, instead of calculating just simply the height function, as you move up the height function, you give a superweight to each node. The sinks get their own weight as superweight. A vertex above it will get the largest of the maximum of the weights of its children. The one above it will get the maximum of its children. And you go up the hierarchy. At the top, when you look at the sources, their superweights will define the heaviest path going from that source to that sink. A heaviest path will be a heaviest clique. So we can see that we solve maximum weighted clique. We can also solve the maximum independent set or maximum stable set problem by using a min flow algorithm and finding a max cut. Now, most of you will have studied algorithms for max flow min cut. It's the same sort of dualized thing, min flow max cut. And if you have a minimum flow, you can find a series of independent vertices that will be the largest that cuts the whole flow in this digraph. What is the complexity of the transitive orientation algorithm? Well, it depends on your data structures as well. The most reasonable and sort of straightforward way would be an algorithm that would have complexity n cubed. Because what would you be doing? What are you doing? You're choosing an edge, you're giving an orientation, and then you have to generate all of the other vertices that might form a V with it, both from this side or from that side. Once you decide what's forced, you can go on and check all of these other edges to see how they are forced. So if you were to look at sort of a vertex, what are you checking? You're checking its neighborhood. And you're doing that for every edge. And you're checking sort of pairs of common neighbors. So each vertex might have possibly n order of n squared pairs that you have to check. Since you do that for any vertex, you have n squared for a single vertex times n vertices. That's basically the complexity. You can speed that up, though, if you notice that you can focus on the edges, and it's not difficult to find a data structure, and you can read this in the book, where you could actually do it in n times e, the number of edges, which, if this is a sparse graph, e might be lower than n squared. But there is a faster algorithm, which only when you go into really advanced algorithms by Ross McConnell, that can actually do it in even less time than that. But we won't cover that algorithm. Now I'd like to move on to permutation graphs. Permutation graphs are a kind of intersection graph, and we'll define them as follows. Let's take a permutation pi of the numbers 1 through n and define its permutation graph as follows. For each of the numbers 1 through n, I will take a vertex of my graph, and I will create an edge when any two numbers are reversed in their order by the permutation. So, for example, let's look at this permutation. What's reversed? Well, 4 and 3 are in the wrong order. They are reversed, so there should be an edge between 4 and 3. And indeed, between 4 and 3, I have an edge. 5 and 1 are reversed, so there's an edge between 5 and 1. But 3 and 5 are in the correct order, so there should be no edge between 3 and 5, indeed. And similarly, 2 and 1 are okay, so there's no edge, but 3 and 2 are reversed. Now notice how I can see this in a diagram, which I've drawn on the slide. In this diagram, I've written the numbers 1 through 5 on top, and the permutation itself on the bottom. I've connected them with straight line segments. And of course, if two numbers are reversed numerically, their segments cross. And if they're in the same order, then their segments don't cross. Okay? You can easily see that on the diagram, but it also makes sense. If I have A here and B here on top, and A here and B here on the bottom, they didn't cross. They're in the same order. But if they got reversed, I have a cross. So the intersection graphs of segment diagrams like this is exactly the same problem as looking simply at the numerical reversal. So I say that I have an edge between two of the numbers when their segments cross in the permutation diagram. And this beautiful theorem by Pnueli, Lempel, and Evin says that a graph is a permutation graph if and only if both G and its complement are comparability graphs. A very beautiful theorem. Now you can imagine many applications of these permutation diagrams. For example, in this illustration, suppose I have airplanes that are flying, say, along these routes, from Chicago to Louisville, or from Des Moines to St. Louis, or from Omaha to Louisville, or New York to St. Louis, etc. Well, these paths cross. And if you conceptually think of the airplane choosing an altitude and flying, you would very much like them to be at different altitudes if they were crossing paths, because you really don't want to crash. And so that can be extracted, this picture, into this permutation diagram. And what would we say? It would be an assignment of altitudes so that crossing paths do not get the same altitude. Call an altitude a color. And so coloring these segments so that intersecting segments do not have different colors solves my problem, and it would be a coloring, a vertex coloring of its permutation graph. You could also imagine a similar application where these were, say, electrical wires on some VLSI chip trying to connect pins on the top to pins on the bottom, and if they cross, you need to give them different layers. The VLSI problems, of course, are more complicated than this, and you actually do other kinds of routings where you don't necessarily run a straight line, but you might do lines that go vertical and horizontal, but that opens up a different ballgame. I'll talk about a problem motivated by that as well next week sometime. Well, if I wanted to recognize permutation graphs, I could just use my algorithm to test the graph and its complement. There are, in fact, faster algorithms to recognize whether you have a permutation graph and to define and to find that permutation. And there again, it would be Ross McConnell that would be largely responsible for having lowered the complexity, in fact, for that problem to n squared. Now I would like to ask, what about coloring? Because coloring is one of our major problems, optimization problems, on all of these classes of graphs. Now, on the one hand, we could take the algorithm that we just learned for transitive orientation and use it for a permutation graph. We could do that because we could take permutation graph. By the theorem, it's comparability. Give it a transitive orientation and call that subroutine, and that would be fine. I could pay n squared or n cubed for that, probably. Maybe n squared log n, or maybe n times the edges, whatever. But if I have a permutation graph, I can actually do it more efficiently straight away. And I'd like to show you how you do that given the permutation. So this algorithm uses what we call a network of k queues in parallel. These are queues. Things go in at one end and come out at the other end. And they are acting in parallel. My coloring algorithm is going to do the following. I'll load my permutation pi on the right side, on the input queue. And I'm going to unload them on the output queue. So we often think of this as saying a railroad train, where each car has to be painted, and they have to be reordered. So you might have them go through a network like this, where you pull one car onto Q1, one car into Q2, and then pull it off. So for example, if you had 2 in front of 1, how would you get them switched around? Well, one way would be take 2, 1, put 2 up here, put 1 over here, pull off 1, and pull off 2, and then they would be sorted into their correct order. Well, this algorithm, using parallel chords, which you sort of are using as an analogy, would be used to sort the pi into its correct order. Let's see an example. But before you see an example, this is the claim that I'm going to be showing you. That the chromatic number, the minimum number of colors needed to color the permutation graph, will turn out to be the minimum number of queues required to sort pi. And the length of the longest decreasing subsequence will also be equal to that number. So I like to think of my network here as the numbers come in. Each queue has a painter with a different color. And if car goes into Q2, it gets painted color 2, and out it comes. So not only I'm sorting it, but in the process of sorting it, I'm also going to be painting the cars the color of its Q. Here's an example. Let's start with this permutation. 4, 3, 6, 1, 5, 2, and put it in the input. Well, 4 I will put on the first Q. 3, which comes next to it, if 4 is already here, 3 comes through here, I better not put him on for first Q or he'll get stuck. So I have to put him on a different Q. I put him on number 2. Number 6 can go on either the first one or the second. My rule will be I'm going to put him first fit. Then comes 1. 1 will get stuck behind 6. It will get stuck behind 3, so it opens up a new Q. Now comes 5. It cannot go on behind 6, but it can go behind 3, so I put him there. And lastly, 2 comes in. He would get stuck behind 6, stuck behind 5, but he's fine following 2. So I've succeeded in lining them up correctly. And now I can pull them off. I pull off 1, pull off 2, pull off 3, 4, 5, and 6. So it's clear that I can sort this permutation using 3 Qs. Notice also that I needed 3 Qs for this. Why might that be? Well, like many of our proofs for optimal coloring, I use the phrase, look at the time when the first color, when the highest color is first used. In this example, 1 was used to open up color 3. What was the situation at that moment? Why was he forced to be on a new Q? So 1 was forced, looking back on my history, because in its iteration, when 1 had to open here, the reason was that 3 was above him blocking. And why did 3 get here? Because when 3 got pushed here, 4 was blocking. So if I follow this chain of who caused me to go to the next Q, 1 was forced by 3, 3 by 4. And now if I look, in fact, at my sequence, I see 4, and then 3, and then 1. 4, 3, 1, it's a decreasing subsequence, length 3. That forms a clique. In the diagram, I would have 1, 3, 4 on top. I would 4, 3, 1 on the bottom. They would cross each other. So that is sort of a witness of why I would be required 3. I succeeded with 3. It's optimal. So, in fact, I'm using this kind of observation that if I look at the last guys in each of the Qs, they always are a decreasing subsequence. And that's what I found here. So what we've just basically proven is that this greedy top-down, first-in algorithm for coloring is optimal. And in fact, the sorting of it was just an excuse to color. I'm not really interested in sorting it. Okay, so why was this optimal? Because we were able to find a clique of that size. So now what we've seen today is that we have the family of comparability graphs, transitively orientable. We've seen that permutation graphs is a subclass of it. And what we already know from the first lecture is that the complements of interval graphs were comparability graphs. So we see these as 2 subfamilies of comparability graphs. When you have an algorithm that works for a parent class. You can always pull it down and use it for the child, but you might find a more efficient algorithm for the child than what worked for the generality of the parent. A class that is below these two classes is the class of threshold graphs, and perhaps we will talk about threshold graphs next week in the context of different other subclasses of interval graphs and of comparability graphs. And we will also talk about another class called the cographs, which fit somewhere between permutation graphs and threshold graphs. And with them, we are going to see an interesting application for circuit design. So that's all, folks, for today's lecture. Thank you very much, and see you next time. Cut. So this was a much shorter lecture than